Hi, this is Nathan, and the next video I want to do on MLE is the normal distribution with unknown variance and unknown mean. So again, the PDF of a normal distribution is going to be 1 over square root 2 pi sigma squared e to negative 1/2 xi minus mu squared over sigma squared, right? So the joint PDF L, and since we have two variables that we want, or two parameters we want to estimate, variance, so sigma squared, and mean, so mu, we have the likelihood of mu and sigma squared, and then we write x, is going to be still the joint PDF of the samples. So product from I equals 1 to n of 1 over square root of 2 pi sigma squared e negative 1/2 xi minus mu squared sigma squared. Or log likelihood, L is equal to the sum of the logs of 1 over square root 2 pi sigma squared, go ahead a step, plus the log of e to negative 1/2 xi minus mu sigma squared, right? Which is equal to, just gonna simplify these logs down a little bit, the sum of, now note that, side note, 1 over square root 2 pi sigma squared is equal to square root 2 pi sigma squared to negative 1, which is equal to the 2 pi sigma squared to the negative 1/2 power, right? So if we want to take the log of this, we get negative 1/2 times ln of 2 pi sigma squared. So that, putting that here, we get negative 1/2 ln 2 pi sigma squared plus this log and this e will cancel out, so we get negative 1/2 xi minus mu squared over sigma squared, right? Now the trick with having two variables in this likelihood function is that now the next step, which is to take the derivative, right? We will be taking two different derivatives. We'll be doing one with respect to mu and one with respect to sigma squared. So let's start with mu. So the partial derivative with respect to mu of this log likelihood, which is actually exactly what we did in the last video. So I'm gonna skip a couple steps there. Watch the last video if you're stuck on that derivation. It's going to get us that mu hat MLE is equal to sum of xi over n, which by definition is equal to x bar, right? So then the second derivative that we take is the partial derivative with respect to sigma squared. Note that we're doing sigma squared and treating sigma squared as a variable instead of just sigma. That is because this derivative is going to be easier to take if we do it with respect to sigma squared, but more on that at the end. So the partial of the log likelihood function with respect to sigma squared is going to get us the write out what the log likelihood function is. Right, and we can, I'm gonna first distribute in this summation. So we have the derivative with respect to sigma squared of negative n over 2 ln of 2 pi sigma squared minus 1 over 2 sigma squared sum of xi minus mu squared, which is equal to, now ln of 2 pi sigma squared is equal to ln of 2 pi plus ln of sigma squared, right? And now the derivative of this with respect to sigma squared is equal to 0. The derivative of this with respect to sigma squared is equal to 1 over sigma squared. So multiplying this by negative n over 2, we have negative n over 2 times 1 over sigma squared minus 1 over 2 sigma squared squared, and now the negative becomes a positive, sum of xi minus mu squared. Now we're setting this equal to 0 to find a maximum, right? So we have negative n over 2 sigma squared plus 1 over 2 sigma squared squared, sum of xi minus mu squared. Is equal to 0, right? Now we can move this over and we get n over 2 sigma squared is equal to 1 over 2 sigma squared squared times sum of xi minus mu squared. Now we can multiply both sides by sigma squared squared. So sigma squared squared, sigma squared squared, that's going to cancel this out, and one of these two is going to cancel out, and we're left with n sigma squared is equal to sum of xi minus mu squared divided by n, and we get sigma squared is equal to sum of xi minus mu squared over n. Now the problem that you may see here is that mu is an unknown parameter that we're estimating. But what we can do with maximum likelihood estimation is, since we found earlier the maximum likelihood estimator for mu, which is x bar, we can just plug that in here. So we have mu hat is equal to x bar, and then that leaves us with sigma squared hat MLE is equal to the sum of xi minus x bar squared over n. So I said before I ended this video that I would talk about why we took the derivative with respect to sigma squared instead of sigma. Short answer is, I'll write this down. Why sigma squared? It's easier. You would get the exact same result if you did this derivative with sigma squared, but if you remember from the exponential example, we have that if sigma squared is equal to sigma squared, right? So sigma squared hat MLE is equal to sigma hat MLE squared. So by finding one of those two MLEs, we actually have both of them.